Welcome everyone to this explainer. Let's just jump right in, because today we are unpacking the world of computational thinking. We're going to define what it actually is, develop strategies to solve problems that leverage the power of technology, and discover new digital resources to really refine our prototypes. And as you'll see, this is absolutely becoming a fundamental literacy for everyone long before a computer ever even gets turned on.
Okay, so here is our roadmap. We're going to cover the problem-solving imperative, clearly define computational thinking, break down its 4 core pillars, do a little unplugged problem-solving, see exactly how coding acts as a translator, and finally, look at some digital tools in prototyping. Let's get to it.
Section 1. The problem-solving imperative.
You know, Seymour Papert, who is a total pioneer in educational technology, really hit the nail on the head here. He pointed out that modern work requires independent problem-solving skills. The world is shifting, right? It's moving away from just memorizing facts and shifting toward building the mental tools we need to actually tackle the unknown.
And what's really fascinating about Papert's philosophy is how deeply human-centric it is. It's not actually about the hardware. It's not about the computer itself. The ultimate goal here is empowering confident decision-makers. The technology? No, that's simply the medium we use to get there.
So let's move to Section 2, Defining Computational Thinking.
So what is it actually? Well, it turns out it's largely a cognitive process. It's literally a way of thinking that we've borrowed from computer science, but it is applicable everywhere. Honestly, whether someone is studying programming, data science, or even the humanities, these problem-solving frameworks are completely foundational. It is for everyone.
And you can really see how this maps out a cycle of powerful learning. On the left side, you've got these cognitive skills, things like recognizing patterns or doing iterative testing, and those feed directly into the practical applications on the right, which is what allows us to automate procedures, analyze data, and model entire complex systems. It's a continuous, cyclical process.
Section 3, The 4 Pillars.
To really make this actionable, we break it down into 4 foundational pillars. First up, decomposition, taking a huge, overwhelming problem and just breaking it down into smaller, manageable chunks. Next, we have pattern recognition, looking for familiar patterns based on things we've solved in the past. Third is abstraction. This is huge. It's where we cut out the noise and ignore irrelevant details so we can focus on what actually matters. And finally, algorithm design, setting out clear, step-by-step rules to get the exact same outcome every single time. And hey, algorithm is really just a fancy word for a repeatable set of instructions.
Section 4, Unplugged Problem Solving.
Let's completely unplug for a second, because I want to prove how often we use these concepts completely offline. Try a quick game of Guess That Movie with me to test out our abstraction skills. Okay, so if I give you clues like time heist, prune face, finger snap, troublesome gems, and RDJ, well, isolated, those details seem incredibly abstract, right? But if you apply abstraction, meaning you ignore the irrelevant info and focus strictly on the connecting pattern, it leads us right to the solution: Marvel's Avengers Endgame. You literally just used a core pillar of computer science to win a trivia game. No screen required. Here's another awesome way this translates to the physical world. This pixel puzzle uses nothing but crayons and a paper grid. It beautifully demonstrates pattern recognition and sequencing without needing a single digital device. It just proves that logical sequencing starts way before anyone ever touches a keyboard. We can even practice algorithm design offline using something as simple as doodle art. By setting up recursive rules, where each step simply tells you to draw the next step in the exact same way, we can actually create a growing, branching plant through pure logic. It just goes to show that if a process can grow or repeat, it can absolutely be turned into an algorithm.
Section 5, Coding as a Translator.
So this is exactly where coding enters the picture, because electronic devices, your cell phone, your laptop, smart TVs, they don't speak human language, right? Coding acts perfectly as our translator. It takes our human-designed algorithms and converts them into the numerical sequences that computers actually require to function and complete tasks, whether that's changing a font color or navigating a complex digital maze. Section 6. Digital Tools and Prototyping.
When we do transition to hardware, tools like the Sphero Indy are incredible at bridging that gap. It's this clever little color-sensing vehicle that lets early learners build physical mazes. Right out of the box, it encourages problem-solving and basic programming through screenless, imaginative play. It's just a brilliant way to test out solutions in real time. And then, as learners are ready to transition to screens, there's a whole world of digital resources to explore sequencing and algorithm design. You've got platforms like code.org, Scratch, and tons of block coding apps that allow students to reconfigure how robots and virtual objects respond to different inputs.
Ultimately, by getting hands-on with these platforms, you get to step right into the role of the facilitator. You manage the environment, guiding your students as they iteratively test, debug, and refine their prototypes. You are giving them the perfect sandbox to challenge themselves within a true cyclical design process.
So we've traced this incredible journey, right? From paper and crayon concepts all the way up to digital block coding. And it leads me to ask, what is the very first step you will take tomorrow to bring this cyclical design process to your own learners? Think about it. And thanks so much for joining me for this explainer.